5. We've done addition. Now we have to identify a multiplicative identity and verify the multiplication axioms for a field. It's interesting because Rudin says that the proof of the multiplication axioms is virtually identical to the proof of the addition axioms, so he omits them entirely from his construction of the real numbers. That's all he says is, oh, they're virtually the same, so I'm not gonna do it. And the truth is, they're not that way at all. They are way more difficult for a reason that I'll show you in a second. So the first issue is that we can't even do multiplication in one step, because multiplication, we've talked about this before, but multiplication it's almost the same as addition, but when you put a multiplication operation together with an addition operation in a field, then it gets way more complicated. And so the problem with multiplication is that there are negative numbers. So you can, if we have a cut, and here's 0, you can add 2 cuts no matter what they are. It's no problem. Then it's just everything in one plus everything in the other, and together they make the sum. The problem with multiplication is included, like let's say that this number right here is 1. Then -2 and -3 are in this cut, but if you multiply these together, you end up with 6. So, like if you had, I guess, here what I'm trying to say is, so let's say we had b is 2. So if we wanted to multiply alpha times beta, the answer should be 2. But what we'll end up with if you include everything is you can't just multiply everything in alpha times everything in beta. Because of negative numbers, you end up with -3 times -2, which is 6, which is way outside what we know the answer should be. So we have to do it in a more careful way. So to begin with, we're going to confine ourselves to just alpha an element of, whoops, I'm sorry, I don't know what I'm doing. Alpha an element of the positives. So we're going to start looking at just positives. We'll establish the multiplication axioms for positives, and then we'll look at what happens in the other cases when it's a minus versus minus times a positive, or negative times a negative. Okay, so if alpha is an element of R plus, beta is an element of R plus, we define alpha beta to be the set of all P such that P is less than RS for some choice of R element of alpha, S element of beta, and R is less than, or I'm sorry, R greater than 0, S greater than 0. So notice again, this is a little bit different than it was for addition already, because we can only we're only looking at the positive elements of alpha and beta. So P is the set of all of the positive elements of alpha times the set of all the positive elements of beta. So P is everything less than those. So it's a little bit different than addition was. And we define one to be the set of all Q less than 1. So with this definition, the axioms of multiplication hold for R plus and with 1 star in the role of 1 as the multiplicative identity. Okay, so I want to talk for just a second about why it's harder, because if you remember, we said once before, we talked a little bit about how the numbers under addition are isomorphic to the positive numbers under multiplication. And the reason for that is that you can just look at the exponents. So for instance, if you have two numbers, say EX and EY, you multiply those together and it equals e to the x plus y. And so you can represent any real number as any base or any positive base raised to anything. And so all of the addition and the multiplication are isomorphic. So given that, one would think that yes, this is going to be easy to prove. And so what we're looking at here is basically, if this is 1, then if we just look at y here is r plus, instead we could look at, instead of the values of y as they go up, look at as the exponents of something, say e. So e to the x goes from negative infinity to positive infinity, then you add those and you'll end up, you're always going to be in r plus. And then, so everything has its analogy. So for instance, with positive, the inverse of a number x is minus x. The inverse of x equals 0. In multiplication, it's division, and we say that x times 1 over x equals 1. But we could rewrite this using exponents. It's x to the 1 times x, x to the 1 times x to the minus 1, that's 1 over x, equals 1 minus 1 equals x to the 0 equals 1. So it looks like everything works the same, with 1 in the position of 0. So we have here that if we're looking at just the reals, the positive reals, 1 is the identity, and everything on this side has an inverse on the other side. Everything on this side of 1 has an inverse on the other side of 1, and all of this is above 0. So all these numbers, basically, what we're talking about, they basically don't exist. So everything from here down has an inverse on the other side. And then if you look at the exponents instead, you could add the exponents, and then everything from 0 down, all the negative exponents, have an inverse on the positive exponents. And here we're just talking about, like, if you have, we'll say that's 2, then its inverse is going to be over here at 1/2. Okay, and so on. So as this goes up to infinity, this gets closer and closer, infinitely closer to 0. So we're going to be able to start by basically just looking at the exact analogy from addition, with, whereas in addition and subtraction, and multiplication you use an inverse instead of a minus sign. The problem with this is exponents, because in the proof of the addition, there comes a point where we take a number and we divide it by 2. Now in the rationals, you can always do that. If R is an element of Q, you can always divide it by 2. But what's the analogy for dividing something by 2 in multiplication? It's a power. It would be instead of r times 1/2, it would be r raised to the 1/2, which is the square root of r. But the whole problem is, the entire reason that we're even here talking about this and trying to construct these numbers is that this more than likely doesn't exist in the rationals. This is why we need real numbers. So we grind dramatically to a halt by the end of this proof. And I'm going to prove everything today up until the very last step, which is where we've got to use roots. And so we're going to have to figure something out to do this. And it's why Rudin is just completely wrong when he says that the proof of the multiplication axioms is analogous to the proof of the addition axioms. So for now, we're just going to do as much as we can, knowing that we have a giant square root coming up here that we want to be in the rational numbers, which can't be. So we're going to have to figure out something else. Okay. So for now, the multiplication axioms. M1 is closure, which means that if alpha is an element of R, beta is an element of R, then alpha beta is an element of R, okay? So what we have to show is that just means that we have to show that alpha beta is a cut. There are three properties of cuts, so we just have to establish that each one of them is true. The first one is that alpha beta, the set of rationals, alpha beta is not empty and it's not all of the rationals. So it's clear that alpha beta is not empty because alpha is positive, so it contains some rational number. Beta contains some rational number. Multiply those together, so it has something in it, so it's not empty. To prove that it's not all of R, take R prime not an element of alpha and S prime not an element of beta, then R prime S prime is greater than RS for all choices of R and S. Therefore, R prime S prime is not in alpha beta. So R prime S prime is not in alpha beta because it's bigger than RS for all choices of alpha and beta. So it's bigger than everything in alpha and beta. So alpha beta does not equal all of Q. Okay. Okay, so for 2 and 3, pick P an element of alpha beta with P greater than 0. Then P equals RS with R element of alpha, S element of beta, R greater than 0, S greater than 0. Okay, so for 2, so looking at P, element of alpha beta, if Q is less than P, then Q is less than RS. That implies that Q divided by S is less than R. So if Q divided by S is less than R, then Q divided by S is an element of alpha. That is property 2, right? Because if we know that R is in alpha, then everything less than R is also in alpha. So if Q over S is less than R, then Q over S is less than alpha. Then we have that Q equals Q over S times S. So we just showed that this is in alpha. We were given that S is in beta. So this is an element of alpha beta. So Q is an element of alpha beta. That's 2. Because we started with P is in alpha beta. We took something less than P and we showed that it's also in alpha beta. That's the definition of 2. So 3, choose T, element of alpha with T greater than R. Then TS is an element of alpha beta, right? Because T is an element of alpha, S is an element of beta. And TS is greater than P. So this is 3, right? You start with an element of alpha beta. You find an element bigger than that element and show that it's also in alpha beta. That's 3. Okay, so we've shown closure that if alpha's in R plus, beta's in R plus, then alpha beta is in R plus. Now the next two, commutativity and associativity, are just like in with addition. They're very easy. Commutativity. So if alpha beta is the set of all RS with R element of alpha, S element of beta, if that's alpha beta, then by the same definition, beta alpha is all SR with. And we know from the axioms of multiplication that RS equals SR. So alpha beta equals beta alpha. And the same thing's true with associativity. If we have that alpha beta is all RS and gamma is all T, then alpha beta is all RS and alpha beta parentheses gamma is all RS times T. But by the same token, beta gamma is all ST and beta gamma in parentheses times alpha is all R times ST. We know from multiplication of rationals that RST equals R times ST. So alpha beta gamma equals alpha beta gamma. Okay, easy. Now it's going to start getting harder. Okay, so first we have to show multiplicative identity. Which we defined as 1 star, which is the set of all rationals less than 1. So what we need to show is that alpha times 1 star equals alpha for all alpha. How do we prove that two sets are equal? We prove inclusion in both ways. So first we have to prove that alpha times 1 is a subset of alpha. Then we have to prove that alpha is a subset of alpha times 1. Okay, 1. So if R is an element of alpha, always with R greater than 0, we're only talking about positives, and S is an element of 1, again with S greater than 0, then with these definitions, then RS is an element of alpha times 1. And if R is an element of alpha and S is an element of 1, then RS is less than R. Because we know that S is less than 1, and this is straightforward now. We've done this many times, but just to verify, S is less than 1, we're given that. Then if you multiply both sides by R, you get RS is less than R. Okay, so RS is less than R. That means that RS is an element of alpha. This is from number 2, right? Because we started with R is an element of alpha, and then we found a number less than R, so by 2, RS has to also be in alpha. Okay, that's number 1. Right here. So now to do the other inclusion, pick P element of alpha and R element of alpha with R greater than P. This is 3. Right? So just whatever P is, find an R that's bigger than P but still in alpha. Then P divided by R is an element of 1. Why is this? Because we have that this is the analogous situation for addition. If we have that R is greater than P in addition, and then you subtract both sides, you get that R minus P is greater than 0, right? We're doing the same thing but with multiplication this time. So if we have that R is greater than P, if you divide both sides by 1 over R, then you get that 1 is greater than P divided by R. And that means that it is an element of 1 star. So P divided by R is an element of 1. And P equals R times P divided by R, right? Because the R's cancel. And this is an element of, so R is an element of alpha. P over R is an element of 1. So this is an element of alpha times 1. So we started with something that is in alpha, and we showed that if that's the case, it's also an element of alpha plus 1, or alpha times 1. So alpha is a subset of alpha times 1. That is inclusion number 2. So we're done. Alpha equals alpha times 1. That means that 1 is the identity element of R. Okay, good.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.